Welcome to the video lesson for section 7.5, matrix operations. We're going to explore what it means to be a matrix and what it represents, and then discuss how to identify when you can add, subtract, and multiply various matrices. Let's get started. To begin with, let's discuss what a matrix actually is. So for our definition, we have for two positive integers n and m, an m by n matrix is given by the following diagram, where we see we have entries, and these entries are going to represent usually different values, integers, fractions, or decimals. And then it is, again, it's an m by n matrix. So we have m rows, which are your horizontal rows, and then n columns are vertical. So if I want to read some of these subscripts, for example, A32, that is an element that's in the third row and the second column. So I would go down 3 and over 2, and I now have my A32. If I had A13, that's going to be in the first row and the third column. So for your subscripts, the first number is going to tell you the row it's in, so how many times we go down, and then the second value is going to tell you just your column, or how many times we go over. One of the nice things about a matrix is it does help collect and organize information and make certain processes a little more organized and easier to do. Just a little more clarity, for a matrix, it is again a rectangular array of real numbers. If we look at our first matrix here, matrix A, we can see that it has two horizontal rows and it also has three vertical columns. So this would end up being what we would call a 2 by 3 matrix. Again, because we have two rows and three columns. When we're talking about our entries, we can identify the position. So for value number 7, if I were to go ahead and circle that, 7 is going to be in row 2 and column 1 because we're going to go down to the second row and then we go over into our first column. So we could call that A21. For our next value, -2, we can see -2 is in that top right corner, and it's going to be in row 1 and column 3 because again we go down to the first row and over to the third column. So if I want to identify its position, I could say that is in A13. Another common term when referring to our matrices is something called the order. So for our definition there we can say a matrix with m rows and n columns is of order m by n. So when we're talking about the size of a matrix, it's more common to talk about the order. Again, we discussed that our matrix A is 2, 3 because it has two rows and three columns. If we ever have the occasion where m and n are the same value, then we have a square matrix of order n. One of the main applications of a matrix is taking a system of equations and organizing it. So for example, here you can see we have a system of linear equations with x, y, and z variables, and we've taken only the coefficients from our system and put them into our matrix. So again, we've collected some values or some information from our system and organized it into our matrix. By doing it in such a way, we can identify our solutions through different operations for x, y, and z. If we wanted to talk about the order of our matrix, we can see that we have 3 rows and we have 4 columns. So we have a 3 by 4 matrix. And again, while this is one of the main applications, we're not going to spend too much time focusing on this. We're going to transition now into the operations we can do once we have something as a matrix. Our first operations are going to be addition and subtraction. So if we want to add two matrices together, we're going to add or subtract elements that are in corresponding position. So it's very important they're in the same spot. So for example, I could take A21, I can add it or subtract it to B21, which would be the element in a different matrix that's in the exact same spot. Another really important thing is you can only add or subtract matrices that have the exact same order. So if they are not the same size and shape, you cannot add or subtract. And the reason is you might have an element that doesn't have anything in another matrix to add or subtract with, which would then violate the rules of adding and subtracting our matrices. To further clarify addition or subtraction, let's look at some matrices here. We have A and B. Now A is a 4-4 matrix, and I know that because there are 4 rows and there are 4 columns. B is also a 4 by 4 matrix because it also has 4 rows and 4 columns. So if I wanted to add or subtract, I have to make sure I'm adding or subtracting elements in the same position. So I could add or subtract A11 and B11 together because again, they are both in the same spot. They're both in the very top left corner. I could also go ahead and combine A21 and B21 because again, they are in the exact same location. And to further clarify, I could combine A43 and B43 because they are also in the same position. And again, because these matrices have the exact same amount of entries and they're the same order, we could go ahead and add or subtract all of the elements together to get the sum or difference of our two matrices. All right, for our first example, we're going to go ahead and add A and B together. So we're going to line up elements that are in the same position. To begin with, my first element in A, this 1, is in the top left. It is the A11 element. So I would add that to the B11 element and so forth. I'm again going to add corresponding elements in the same position. So we can kind of see that here. Again, I have A11 and B11. Then I have A12 and B12. And then A21, B21, A22, and B22. So I have all the elements in the same position. When I go ahead and finish simplifying that, I get my final answer of 4, -2, 8, and 6. So again, just to illustrate, I'm adding elements in the same spot. So I took the 1, added it to the 3. I took the 2 and added it to the -4, and so on. For our next example, we're going to go ahead and subtract. We're going to do A minus B. Very similar process as the last example. We're going to be subtracting things in the same spot. So instead of doing 1 plus 3, I'm going to do 1 minus 3. And we can see that instead of 2 plus a -4, I did 2 minus a -4. And same thing with my second row. I did 3 minus 5, and then -1 minus a -7. And we end up with our final answer of -2, 6, -2, and -8. All right, we're going to take those same two matrices, but this time we're going to do B minus A instead of A minus B. So instead of doing 1 minus 3, I'm going to do 3 minus 1. And then instead of doing 2 minus -4, we'll do -4 minus 2. We can see that illustrated here. So again, we're doing B minus A. And then we go ahead and simplify things. We end up getting 2, -6, 2, and 8. And now if we think about this answer and what we got with A minus B, it turns out that they are exact opposites. So if we switch the order of subtraction, then we basically are changing the sign of every element in our resulting difference. All right, in this example, we're going to go ahead and try and add matrices A and B together. So I can see that I can definitely add the 1 with the 3. I can add the 2 with the -4. The problem here is I don't have anything to add with this 5 over here. And the reason being, again, my matrices are not of the same order. You can see that matrix A is a 2 by 2 because it has 2 rows and 2 columns. But matrix B is a 2 by 3 because it has 2 rows and 3 columns. And since they do not have the same number of columns, then we aren't going to have our elements lining up, so we can't actually add these together. So our answer is just undefined or not possible. For scalar multiplication, this operates the same way as it did with our vectors. We're going to take a scalar value and multiply it by our matrix, and we're going to actually multiply it by all elements of the matrix. So for example, if I wanted to go ahead and multiply my matrix by 2, you can see that I have 2 times every element in my matrix, and the resulting matrix would again just be every element multiplied by 2. For our example with scalar multiplication, we're going to go ahead and find sum of 3a and 2b. So my first step is to go ahead and do the multiplication. I want to identify what 3a is and what 2b is. To find 3a, I'm going to take each one of my elements and multiply it by 3. And then to find 2b, I'm going to again take each one of those elements and multiply them by 2. And I can take my resulting multiplications and add them together. So I would have 3 plus 6, and then I would have 6 plus a -8, and so on. And when I simplify all of that, we end up getting 9, -2, 19, and 11. Again, though, the first step here was to go ahead and do our scalar multiplication, get those answers, and then add them together to finish getting our final sum. For our next example, we're going to go ahead and do 3b minus 2a. Again, I'd like to go ahead and start off by doing my scalar multiplication. So I'm going to identify 3 times b and also 2 times a. So you can see we've done that here. We have 3 times everything in b, and then we also are going to have 2 times everything in a. When I'm doing my subtraction, I'm going to end up having 9 minus 2, and then -12 minus 4, 15 minus 6, and finally 21 minus a -2. And we get a final answer of 7, -16, 9, and 23. All right, moving on to matrix multiplication. First thing we want to identify is when we can and cannot multiply, and then if we do, what the answer will look like. So for the size of your product, if A is a matrix of m by n, and B is a matrix of n times p, then your final matrix is going to be an m by p matrix. So to kind of highlight that, what we're going to end up taking is the number of the number of rows of our first matrix and the number of columns of your second matrix, and that's going to end up being the size of your next matrix. One thing that's really important to note though, when we're multiplying, we have the same amount of columns for our first matrix as we do of rows for our second matrix. Let's look at an example here. So we have matrix A, which is a 3 by 2, and we have matrix B, which is a 2 by 5. First thing we have to check is that we can actually multiply these together. So if you look at the number of columns of your first matrix, there are 2. And the number of rows of your second matrix, there are also 2. So these numbers are in fact the same, and they have to be. Once you've identified that those are the same, then the size of your matrix is going to be the number of rows of our first matrix by the number of columns of our second matrix. So we're going to end up having a 3 by 5 matrix. Looking at the second example, we have a 3 by 4, and we want to multiply that by another 3 by 4. So the first check, the number of columns of our first matrix and the number of rows of our second matrix. Those numbers need to be the same. In this case, they are not the same. And since they are not the same, you can't multiply those two matrices together. All right, so we have a couple examples here. We're going to go through quickly and see if we can find the order of the product of our two matrices. I apologize, the bottom one got cut off, but we'll get to that in a second. For our first product, we have a 3 by 3 and a 3 by 2. When we line them up in this order, we can very quickly check to see if the two inside numbers are the same. In this case, they definitely are, so the resulting matrix will end up being the size of our outside numbers, which means we're going to end up having a 3 by 2 for our final product. Looking at our second example, we can see that the two inside numbers are in fact not the same, and since they are not the same, we can't multiply this together. It's not possible. Moving on to example number 3, we can see, again, since we line them up, the inside numbers are in fact the same. And since those are the same, our order is going to be the size of our outside numbers, which means we're going to end up having a 1 by 3 for our final answer. For our next example, again, we can see that we have the same values on the inside. They are both 5. So when we multiply this together, the order will be the two outside numbers, and we're going to have a 2 by 7. And finally, for our last example, again, I apologize, I didn't quite make it onto this slide, but it is in your notes. If you look at our two inside numbers, we have a 2 by 1. And since those numbers are in fact not the same, your answer for this is going to be not possible. Okay, for our definition of a matrix multiplication, it's a little complicated, but we can see that if A is a matrix of m by n order, and B is a matrix of n by p order, then we have the product is going to be m by p, which we've discussed. And now the way we're going to identify that is we're going to multiply corresponding components together. So I have AI1 times B1j, and then AI2 plus B2j, AI3, B3j, all the way to AIN, BNJ. So this is kind of our formula for how we're going to multiply things together. And I know it's a little complicated, but essentially I'm going to take the first row of matrix A and multiply by the first column of matrix B, and whatever I get as my final answer is going to be the value I plug in the product. Let's go ahead and look at that as an example, which will make it a lot more clear. All right, so I'm going to identify that I can actually multiply these together. Before we do that, we have a 2 by 2, and we have another 2 by 2. These are in fact the same size, so I can definitely multiply them together. The way we're going to do that is I'm going to take the first row of matrix A and the first column of matrix B, and I'm going to multiply things together. Okay, so I'm going to set up a matrix here where I'm going to kind of show my work, and then my other matrix is where my answers are going to be. Okay, so I'm going to take the first element in my row for A and multiply by the first element in my column for B. So I end up getting 1 times 1. And then I'm going to add to it the second element in my row for A times the second element in my column for B. So I'm going to add to that 2 times 3. And I end up getting 1 plus 6, which is 7. So that's going to be my answer in my resulting product. All right, so what I want to do now is I want to go ahead and multiply the first row in A times the second column in V. So I'm going to have my first element in my row, 1, times my first element in my column, which is 2. So I have 1 times 2. And then I'm going to add to that the second element in my row times the second element in my column, so plus 2 times 4, which is 8. And when I add that together, I end up getting 10. All right, so now I've done everything with my first row. I need to go ahead and move on to my second row. So I'm going to go ahead and multiply my second row of A times my first column in B. Again, we're going to take our first element in the row and multiply by the first element in our column. So I get 3 times 1, and then I'm going to add to that my second element in my row times my second element in my column. So plus 4 times 3, and it ends up being 12 plus 3, which is 15. And then we're going to attempt to do the same thing, but instead of multiplying by the first column, we're going to go ahead and multiply by my second column. So I'm going to take 3 times 2, which is going to be 6. And I'm going to add to that 4 times 4, so I'm going to add to that 16. And I'm getting 22. And so my final answer is the matrix 7, 10, 15, and 22. All right, in this example, we're going to go ahead and multiply B times C and then multiply C times B and see if it can establish any connection or not. So when I multiply B times C, again, we're going to do the same process. I'm going to multiply my first row of B times the first column of C. And you can see that we have that here. So I have 1 times negative 1 plus 3 times 4. Then we're going to take that first row and we're going to multiply it by the second column. So I end up having 1 times 2 plus 3 times 0. And then for our next step, we can multiply our second row by the first column in C, where we get 2 times negative 1 plus 5 times 4. And then our second row in B times our second column in C. And when we simplify everything, we go ahead and get 11, 2, 18, and 4. All right, we're going to go backwards now. So we're going to go ahead and attempt to multiply C times B. So I'm going to be taking my rows in C and multiplying by the columns in B, which means I get negative 1 times 1 plus 2 times 4. And then I'm going to go ahead and multiply by my second column. So now I have negative 1 times 3 plus 2 times 5. You can see that we have that here. Once we finish multiplying our first row in C, we can move on to multiplying by our second row in C. So I have my second row times the first column, which is going to be 4 times 1 plus 0 times 2, which we have here. And then finally, we have our second row times our second column. When I simplify, I end up getting 3, 7, 4, and 12. When I compare my two matrices, there's really no way to associate the two. So I have an 11 and a 3. They're not multiples of each other. They're not differenced by a sign or anything. I have a 2 and a 7. So these products are pretty much random in terms of how they relate to each other. So we can definitely say that without a doubt, B times C is not going to equal C times B for any square matrices. All right, in this example, we're going to attempt to multiply matrix A times matrix B. We can see that we have a 2 by 2, and then I have a 3 by 2. So when I check real quick, I can see that my column for my first matrix and my rows for my second matrix don't in fact line up, which means that I can't multiply them together. And let's go ahead and verify why we can't multiply these together. If I take my first row for matrix A and my first column for matrix B, I would get 1 times negative 1 plus 2 times 4, and then I have nothing to multiply by that 5. And since I don't have enough elements to multiply, the rules for multiplication don't hold, and you can't actually find a product for these two. All right, so now we have switched the matrices, and now A is going to be our 3 by 2, and B is going to be our 2 by 2. Since the inside values do in fact line up, we can multiply these together, and we should end up with a 3 by 2 as our final answer. We're going to go ahead and walk through the process to do that. So let me set up some matrices real quick. This will be where I show my work, and then my final answer will end up being over here. All right, so we're going to multiply our first row of matrix A times our first column in matrix B, and we end up getting negative 1 times negative 3, which is 3, plus 3 times 2, which is going to be 6. And when I add those together, I get 9 for my value. I'm then going to go ahead and multiply my first row times my second column. And when we do that, we get negative 1 times 2, which is negative 2. Let's use a pen here. Negative 2. And then we have 3 times negative 4, which is negative 12. And if I add those together, we get negative 14. All right, we're going to switch on to our next column, sorry, our next row. So I have my second row in matrix A times my first column in matrix B. We get 4 times negative 3, which is going to be negative 12, plus negative 2 times negative 1, which is negative 2, and that gets me a negative 14. We're going to go ahead and move on to multiply our second row by our second column. So we get 4 times 2, which is 8, and then negative 2 times negative 4, which is positive 8, getting us 16 as our answer. And then for my last step, I'm going to multiply my last column, sorry, my last row by both columns. So we get 5 times negative 3, which is negative 15, plus 0 times 1, which is going to be 0. So my final answer there is negative 15. And if I take that last row and multiply by my last column, we get 5 times 2 plus 0 times negative 4, getting us 10 as our final answer. All right, we also have what is called the identity matrix. And for our identity matrix, it's a square matrix, right? It's n by n, and it consists of 1s along its main diagonals and a 0 everywhere else. And because it's an n by n matrix, the identity matrix is always of order n. And we can see our notation here. So starting with the top left, we have a 1, and along our diagonal, all the entries are 1 all the way to the bottom right. Everything else in the matrix is going to be a 0. All right, down the bottom for our note, again, just reiterating that the identity matrix is square. And if the order is understood to be n, then you can denote it as I sub n. And we'll talk about a couple different orders of the identity matrix. So here we can see what the 2 by 2 identity matrix looks like, the I sub 2. Again, this is talking about your order or your n value. We have the diagonals of 1, and then everything else is a 0. For I3, something that is a 3 by 3, again, you have the diagonals of 1, and then your other values are going to be zeros. And then lastly, in last example, we have the 4 by 4 matrix. Again, your diagonals of 1s, all other entries are zeros. When multiplying a matrix by the identity matrix, it is the exact same as multiplying by a scalar value of 1. So we can see here the product of any matrix A and the identity matrix is always going to be the original matrix A. So we can see here for our example, if I take my matrix A and I multiply it by my identity matrix I3, after we've gone through the whole process, we end up getting the exact same matrix we started with. So just to kind of verify that, let's just work on this 3 here. If I take my first row and multiply by my first column, then I get 3 times 1, which is 3, plus 2 times 0, plus 0 times 0. So I have 3 plus 0, which results in just 3. And so if I did that with every other element, again, we would end up with exactly the original matrix we started with. All right, guys, that does it for this section. Go ahead and get started with the homework, and good luck.